When we stand under a clear night sky and see those tiny, cold stars, it feels like the universe is just an arm's length away. When we watch a rocket launch on our screens, a bright pillar of fire pushing metal into the sky, it feels like distance is something we can simply burn through with enough fuel. When we scroll past headlines about Mars colonies or tickets to space, another planet can start to feel like the next country over, just waiting for a faster spaceship. When we imagine humans walking on red deserts or floating above cloudy worlds, it feels as if the only thing missing is the will to go. But behind these images, hidden from our everyday senses, lies a universe that is not just far away, but deeply unfriendly to our fragile bodies and our current technology. If we can put satellites around Earth, send rovers to Mars, and probes to the edge of the solar system, why is it still so hard to send people safely to other planets and bring them back? What exactly stands between us and a routine trip to Mars or even a human mission into the deep outer solar system? In this journey, we will peel back the romance of space travel and see the hard limits, distance, energy, radiation, gravity, and the human mind itself. Open your mind. Follow your curiosity. Welcome to the Center for Curiosity. Before we can understand why going to other planets is so hard, we first need to understand just how big our own cosmic neighborhood really is. Here is the simplest way to imagine it. Think of Earth as a tiny house in a huge city. Low Earth orbit, where the International Space Station flies, is like stepping just outside your front door and standing on the porch. The Moon is like the next street over. Mars, Venus, and the outer planets are not just a few streets away, but entire cities away. The distances are so large that even light, the fastest thing in the universe, takes minutes to travel between planets. To cross these distances with real spacecraft, which are painfully slow compared to light, we need huge changes in speed, what space engineers call delta V, the total push a spacecraft needs to leave Earth, travel through space, and then slow down safely at the destination. Every bit of that push costs fuel, and fuel itself has mass, which needs even more fuel to move. This creates a brutal loop where going a little faster or carrying a bit more makes the whole mission suddenly much harder. To see how humans arrived at these problems, imagine the early days of rocketry. At first, rockets were just weapons, simple machines that threw explosives a little farther than before. Visionaries like Konstantin Tsiolkovsky and Robert Goddard began to think of rockets not as weapons, but as vehicles that could escape Earth itself. They discovered a key idea, the rocket equation. This equation showed that to increase a rocket's final speed, you either need a much better engine or you must carry exponentially more fuel, which quickly becomes impractical. In the 1960s, the Apollo program managed to send humans to the Moon by building enormous multi-stage rockets that were mostly fuel with a tiny capsule on top. Even then, the Moon is still within what space engineers call sea-lunar space, close enough that communication delays are short and Earth's gravity still dominates the journey. Reaching Mars or beyond means going far outside this comfort zone, into a region where the journey takes months or years and the safety net of Earth is much thinner. Now, let's look at the core logic of why sending humans to another planet is such a massive challenge. First, distance and energy. Even when Earth and Mars are on the same side of the Sun and relatively close, they are still tens of millions of kilometers apart. A practical mission usually aims for a path called a transfer orbit, which is like merging onto a cosmic highway at just the right time. To reach this path, the spacecraft must climb out of Earth's deep gravity well, gaining enormous speed, then adjust its trajectory in the emptiness between planets, and finally slow down again to be captured by the target planet's gravity. Each of these steps costs energy and fuel, and the more cargo and people you want to bring, the more demanding it becomes. Second, there's the problem of radiation. On Earth, we live under a thick blanket of atmosphere and a strong magnetic field that together block or deflect most of the dangerous particles streaming from the sun and from deep space. In interplanetary space, that shield is gone. Astronauts are exposed to high-energy particles that can damage DNA, increase the risk of cancer, harm the heart and blood vessels, and affect the brain and nervous system over time. Unlike a quick X-ray at a hospital, this radiation is a slow, constant drizzle that can last for months or years on a long mission, and shielding it fully would require heavy materials that are hard to launch. Third, microgravity slowly reshapes the human body. In orbit, astronauts float because they are in continuous free fall, and their bones and muscles no longer need to work as hard to support their weight. Over weeks and months, the body begins to adapt in ways that are not good for life back on a planet. Bones lose minerals and become weaker. Muscles shrink, especially in the legs and back, and the heart and blood vessels adjust to pumping blood in a weightless environment. These changes can lead to bone loss, muscle atrophy, balance problems, and issues with blood pressure when astronauts return to gravity. And the longer the mission, the more serious these effects become. Even the eyes can be affected, with some astronauts experiencing vision changes due to shifts in fluids inside the skull. Fourth, consider the spacecraft itself as a tiny, closed world. Everything needed to keep humans alive, air, water, food, temperature control, waste management, must function perfectly for months or years with no emergency resupply from Earth. Life support systems must recycle almost everything, turning exhaled carbon dioxide back into breathable oxygen, cleaning water again and again, and keeping the cabin within a narrow range of temperature and pressure, all while using as little power and mass as possible. Any serious failure far from Earth is not just an inconvenience, it can be fatal. Then there are the planets themselves. Take Mars as an example. Its atmosphere is extremely thin, less than 1% of Earth's surface pressure, yet still thick enough to create heat and shock when a spacecraft enters at high speed. Parachutes alone cannot slow a heavy lander enough in such an atmosphere, but without any atmosphere, like on the Moon, parachutes would be useless anyway. This strange middle ground makes landing large, crude vehicles on Mars one of the hardest engineering problems in the solar system, requiring a precise combination of heat shields, parachutes, retro rockets, and possibly new technologies like inflatable decelerators. Venus is even more extreme. Its surface is hot enough to melt lead, with temperatures of more than 460 degrees Celsius and pressures similar to being nearly a kilometer under Earth's oceans. Any human lander on the surface would need to survive crushing pressure and intense heat that destroy most materials and electronics in a short time. Gas giants like Jupiter and Saturn present a different kind of problem. They have no solid surface to land on at all, only deeper and deeper layers of gas and liquid, along with intense radiation belts around some of them. For now, humans can only realistically aim for solid or icy worlds with more manageable conditions, and even those are harsh compared to Earth. Beyond these physical and technical challenges lies the human mind. A mission to Mars might take roughly 6 to 9 months one way, followed by a long stay, and then another journey back. That means crews could be away from Earth for more than 2 years, confined to tight spaces with the same small group of people, with no possibility of quick rescue. Isolation, monotony, and the knowledge that Earth is just a distant dot in the window can lead to stress, sleep problems, mood swings, and conflicts, all of which must be managed to keep the crew safe and cooperative. Communication delays add another layer. When Mars is far from Earth, a radio signal can take up to about 20 minutes to travel one way. Conversations with mission control become slow exchanges, not real-time chats, and emergency decisions must often be made by the crew alone. So far, this has been the simple version of the story, but reality is even more complex. Radiation levels are not constant. They spike during solar storms, which can suddenly increase the dose of harmful particles, forcing astronauts to shelter in better shielded parts of the spacecraft. Different types of radiation, such as galactic cosmic rays and solar energetic particles, damage the body in different ways, and predicting their exact effects over years is still an active area of research. Microgravity does not affect all people in exactly the same way either, and new patterns of health changes are still being discovered as missions get longer. Even Mars itself is not a static environment. Dust storms can grow to planet-wide events, darkening the sky for weeks and affecting solar power and visibility. There are also exceptions and partial solutions that complicate the picture. Shorter missions closer to Earth, like those in low Earth orbit, already show that many microgravity effects can be reduced with exercise and careful planning, but not eliminated entirely. Artificial gravity, created by rotating parts of a spacecraft, could help, but building such a system at the right size and speed without causing motion sickness or structural problems is difficult. More advanced propulsion systems, such as nuclear thermal rockets or electric propulsion, could shorten travel time and reduce radiation exposure, but they bring their own engineering and safety challenges. No single solution solves all problems at once. Now comes the deeper, wow, insight. All of these difficulties are not random obstacles. They are direct consequences of the same physical laws that make our home planet so comfortable. Earth's gravity, which holds our atmosphere and oceans in place, is the same gravity that makes escaping into space so energy-hungry. Our thick, protective atmosphere is what shields us from radiation and keeps our bodies adapted to one specific pressure and temperature range. The very things that make Earth ideal for life also make it very hard for that life to leave and thrive elsewhere. When we struggle to design a mission to Mars, we are really discovering how finely tuned our existence on Earth is, and how unusual our planet may be compared with many others. There's another surprising angle: time. Our human lives are short compared to the scale of space travel. Taking years to travel to a single planet feels long to us, but for the solar system, years are nothing. In a way, interplanetary travel forces us to stretch our sense of patience, planning for missions that may outlast political cycles, careers, and even individual lifetimes. This slow, careful pacing challenges how human societies normally do things and demands long-term thinking that is rare in many areas of life. Why does all of this matter right now? Because humanity is standing at a turning point. Space agencies and private companies are actively planning crewed missions to Mars, building more advanced spacecraft, testing new ways to land on alien worlds, and studying how to protect astronauts from radiation and microgravity over longer times. Robotic missions are already scouting landing sites, testing technologies, and sending back data that will shape human journeys in the coming decades. Even if most of us never leave Earth, understanding these challenges changes the way we see our planet, not just as an ordinary place, but a rare, carefully balanced world that supports us in ways no other known planet does. So why is it so hard to go to other planets? Because the distances are enormous, demanding huge changes in speed and careful timing. Because space between planets is filled with invisible dangers like radiation and the effects of weightlessness on the body. Because other planets are not friendly destinations. Mars has a thin atmosphere that makes landing heavy vehicles extremely difficult. Venus has crushing heat and pressure, and gas giants have no solid surface at all. Because life support, communication delays, and the psychology of long isolation all add layers of risk that must be solved together, not one by one. Yet each of these obstacles is also a clue to how the universe works and to what humans must overcome to truly become a multi-planet species. Think back to those moments at the beginning. When you look up at the night sky now, you can see not just distant stars, but the enormous energy and planning needed to move even a small group of humans from one world to another. When you watch a rocket launch, you can imagine the invisible mountain of fuel beneath the tiny capsule and the delicate life support systems inside it. When you hear talk of Mars colonies or missions to other planets, you can picture the thin Martian air, the harsh radiation, and the complex choreography required just to land safely and survive a single day. The universe no longer feels simply far away, it feels real, structured, and demanding, like a vast puzzle that we are slowly learning how to solve. So here's a question to carry with you. If we could magically remove just one major barrier, distance, radiation, gravity, or psychology, which one do you think would most change our future in space, and why? If you enjoyed this explanation, consider subscribing for more curiosity-driven content.